wanted to take you through the second part of my exothermic and endothermic reactions booklet. And this time we're going to look at cells and batteries and fuel cells. I do want to point out this was actually removed from the paper last year, so you never know, it could potentially come up. So if you turn to this page here, which is all about cells. So like I said, we're going to talk a little bit about batteries, how we can create a battery. Essentially, we're going to really break this down in terms of what it is. And then we're going to look at fuel cells, and that then links into the reactivity series. Well, it links into redox reactions, which we've covered in the reactivity series video. So again, I'd suggest you watch that before we look at this, because then it'll hopefully help to make it a bit more straightforward in terms of what's going on. So we're going to start off with the basics, okay? So essentially a cell, okay, contains chemicals that react. So cells contains chemicals that react. And that is what then generates the electricity. So that reaction is what generates the electricity. And we can actually create a potential difference. This is where physics comes into this. So potential difference is, as you'll know it, is called voltage. And that is needed to push the current around the circuit. So you can't have a flow of electrons without a potential difference of voltage. And that can be dependent on several factors. And those factors include things like the type of electrodes we have or we're using, which I'll come to talk to in just a sec, or the electrolyte that we're using. And we talk a lot about electrolytes in the electrolysis video. So again, there's a bit of a link that could be made here. We could actually put these two things together. Now, if I was to create a simple cell structure, essentially all I would need to do is take two metals that are different. So you can see in my diagram, I have got magnesium and I've got copper. And if you look at the reactivity series, they are quite far apart on the reactivity series. So actually I get to create a greater voltage because of that. So a simple cell essentially is two different metals that are in contact with an electrolyte. And like I said, I would definitely suggest you watching the electrolysis video before you kind of come here. But an electrolyte has ions that can move freely within the solution. And I do want to point out that this type of question does, and I have seen it linked to the reactivity series. So again, I would suggest you watch the reactivity series video, where if you've got a greater difference between the metals, so let's say magnesium and copper are quite far apart, then actually I would have a greater voltage change than say zinc and iron, which are really close together. You can see the difference is minimal. So I've seen this link to the reactivity series, so just be aware of that. Now, batteries, as we know it, this is a typical picture of a battery. Batteries are essentially two or more cells connected together. So let's write that down. So batteries are two or more cells connected, and the key thing is knowing that they're connected in series. And again, you cover that in physics, and that is to provide a greater voltage, Now, you do have different types of batteries. You have your non-rechargeable batteries and you have your rechargeable batteries. So we're going to start off with your non-rechargeable batteries. And these are the ones that we would use in the home. these are what we call non-rechargeable, although you do get sometimes rechargeable batteries that look like this. But we're going to talk first of all about non-rechargeable batteries. And these essentially stop working. They eventually stop working. And the reason why is because the chemical reaction stops. So as I said above, cells contain chemicals that react together to generate electricity. In a non-rechargeable battery, that chemical reaction eventually stops. And it usually stops because you've used up one of the reactants. So as such, the reaction stops and we can't replace those reactants. So your alkaline batteries, the ones that you would use like so, your remote controls, for example, are usually non-rechargeable. They stop working when the chemical reaction stops, and that's usually due to the fact that that one of the reactants has been used up. Now, rechargeable batteries. Okay, these can be recharged, funnily enough. And that's because the chemical reaction can be reversed. When you apply an electrical current. So usually for your rechargeable batteries, you might get a little plug socket where you put your batteries in, you then plug it into the mains electricity, and when you apply electricity, it allows the chemical reaction to be reversed and therefore recharges the battery. I do want to point out though, there is a limit on that. Eventually it does stop, which can be a negative. And I have seen questions where they're getting you to evaluate the use of batteries compared to, say, fuel cells. And we'll do that when we come to look at fuel cells, but just be aware that there is a limit. It's not never ending. So the second part of this video, we're going to look at fuel cells. I wish this booklet would have photocopied right, but this is essentially fuel cells. And this is where it gets a little bit complicated because we do need to link it to redox reactions, which I will do. But hopefully I'll make it as straightforward as I can. But like I said, before, if you get any questions, if you're unclear about anything following the video, please don't hesitate to come and speak to me and we can go through it together. So fuel cells are essentially what they say on the tin. These are use a fuel of some kind. So there is an external source of fuel. So an external source of fuel, and the example that we look at GCSE is when we use hydrogen as our fuel source. And we are usually reacting that with oxygen. And that comes from the air. And we get essentially oxidation and reduction reactions happening. And if you've watched the reactivity series video, that is what we call a redox reaction. So where we've got oxidation is loss of electrons and reduction is gain of electrons. It's just keep this in mind when we are talking about fuel cells. So reduction is gain. And I will show you what I mean by that when we come to look at the half equations. So you can see from my diagram, I've got my external fuel source, which is hydrogen, and it's being pumped into my fuel cell. And the fuel cell is then allowing it to react with oxygen. And as a result of that reaction, we then produce water. Here is the oxygen gas being pumped into the fuel cell. You've then got a chemical reaction taking place within the fuel cell, and the byproduct is water from the reaction. So we're going to talk a little bit about what is happening inside the fuel cell, and it's important that you know what's been oxidized, what's been reduced, for example. So the first thing I want to tell you is that the fuel is oxidized. So in this case, this is the hydrogen. Okay, so the fuel, the hydrogen gas going in, is oxidized. Now, we know the basics of oxidation is that means it gains oxygen. And it does that electrochemically, a reaction within the fuel cell that actually produces voltage. Or, as you know it from physics, potential difference. So that therefore will allow electrons to flow, because we need that potential difference in order for current to flow. So the hydrogen gas is oxidized to produce water. And you can see that quite clearly here, that water is a byproduct of that reaction. And this is where half equations come in. Now, this half equations are only for higher tier. So foundation tier, you don't need to know half equations. So again, just fast forward through to the pros and cons of each. But we'll do the half equations now, because I do think it's important that you are aware of what those things are. And we will start with the cathode. So the cathode is negatively charged. So my cathode would be here on the diagram. So I will do a little arrow to show that's the cathode. This is my anode, and we know that from electrolysis. And it will, in fact, undergo, at the cathode, we would generally have oxidation taking place. And oxidation is the loss of electrons. Okay, because that's what oil rig stands for. Oxidation is loss. So I know my hydrogen gas is being pumped in here, and as a result of that, we then have an oxidation reaction taking place. And that then means we've got essentially my hydrogen gas breaking down to form my hydrogen ions. You can see that on the screen. And it loses, in order to turn from an atom into an ion, it has to have lost electrons. And because there's two atoms, there's two hydrogen ions, so it's lost on this side, this is lost here, 2 electrons, which is why that is an example of an oxidation reaction. Okay, at the anode, which we know is positive, we have reduction, which we know is the gain of electrons, because reduction is gain of electrons. And if you look at the diagram, you can see this is where we're starting to make our water. So we've got our oxygen, our hydrogen ions, which are over here, plus the 2 electrons that have came across. And as you can see, they're coming across here due to the potential difference, because we've got voltage, which can push the current. And that's going to carry out a reduction reaction to make water. So we've got oxygen from the air. We have our hydrogen ions from what's happening at the cathode, and it is going to then go to make water. And we know that reduction is loss of electrons, so we're going to have to lose electrons here. So let's just balance this equation. So I can see I've got 2 hydrogens, 1 oxygen. I've got 2 oxygens over here, so I need 2 of those. That then means I've got 4 hydrogen atoms, so I need 4 hydrogen ions. So it's going to have to gain, in total, 4 electrons back. And that is why it's been reduced, because it's gaining electrons to allow it to form the molecule water. So we can actually write that equation a bit more simply, where we have two hydrogens reacting with oxygen to give us two water molecules. So where have I seen this come up? How have I seen this come up? Well, there's a couple of things. I've seen it linked to reactivity series. I've seen it linked to redox reactions. You have to be able to identify what's been oxidized, what's been reduced. You have to be able to write half equations if you're higher tier. But I've also seen these kinds of questions come up where you're having to evaluate. So you know those lovely 6 markers where you're having to evaluate batteries compared to fuel cells, and then looking at how one is better than the other. So we're going to look at essentially evaluating, if you think of this like electrical energy. So you know how we've got a lot of cars nowadays that are switching to electrically powered vehicles, which are batteries essentially. And you could be asked to evaluate the use of battery powered cars compared to normal powered cars in terms of fuel. So again, you might be asked to evaluate that. So we'll look at batteries to begin with, in terms of, for example, in cars. So in terms of the good things and the bad things, so batteries obviously do not release greenhouse gases, so no greenhouse gases. Remember, it's not enough to say no pollution. You have to link it to greenhouse gases. So we're talking like CO2, sulfur dioxide, nitrous oxides. We don't have any of those nasty gases, so that's why it's a good thing. The only byproduct is water, as you saw earlier on in the fuel cells. So actually that's quite a good thing. The difference is, though, is that batteries actually have a negative when it comes to disposal. So in terms of when we dispose our batteries, they actually can give off high, because of the types of metals they're generally made from, they can be highly toxic and therefore polluting to the environment. So the toxins might seep into the ground, for example. Another positive of batteries is the fact that they are rechargeable. Okay, and that's a good thing because that's going to save you money in the long run. But as we've already said before, there is a limit on how many times it can be recharged before it needs to be replacing. And batteries can, in fact, be more expensive to make than fuel cells. So they can be expensive too. Okay. So what I'm actually looking at here is this conventional fuel cells. I mean, your conventional petrol-based cells that we'd use in the car compared to using battery-powered vehicles. So it can be negative in terms of it's expensive in the long run. Batteries also store less energy, which is why they have to be recharged, and they don't generally last a very long time before they need to be recharged. So they store less energy, so they often need recharging, and that in itself can take a long time, which can be a negative. So good things is that it doesn't produce greenhouse gases, therefore global warming, etc. It's rechargeable. In the long run, I might save money because I'm not paying for expensive fuels. But in terms of negatives, the battery itself is highly toxic in terms of its disposal with the metals it uses. There's a limit before I need to replace the battery. So even though I can recharge over time, I have to eventually get it replaced. It's expensive to make, but actually might save me money in the long term. And it stores less energy. So therefore, I have to recharge it and I might not get as far as a result. There's also disadvantages in terms of fuel cells. And I've seen questions come up where they're getting you to think about fuel cells, for example. We talked about hydrogen fuel cells in this section here, where they might get you to compare hydrogen fuel cells to normal fuel cells, which is what we'd use in normal cars. So we're talking like petrol-based cars. And so hydrogen fuel cars do have disadvantages. Obviously, an advantage would be that you don't make greenhouse gases. But disadvantages is the fact that we have a gas, and so these are our negatives, and gases need to be stored, which requires space, which is obviously a negative because we need space within the car to do that. Hydrogen is explosive. It's what powers the sun, for example. So it's dangerous, and therefore, in terms of safety, it's a concern. And hydrogen fuel is often made from hydrocarbons, which obviously has been produced from usually electrolysis and comes from fossil fuels. So made from hydrocarbons, which we know are fossil fuels. You know from paper 2 that these guys are finite, so we're running out of them. And that's a negative thing. And electrolysis of water gives us hydrogen, and electrolysis requires energy, which is also expensive. So usually when you get asked questions around hydrogen fuel cells, you're always given a table with lots of information in it, and it's just been able to weigh up the pros and the cons. So you might be asked to compare a battery-powered car to a fuel-powered car. So when I say fuel-powered, what I mean is your typical petrol cars. Or you might be asked to look at hydrogen fuel cars, and again, being able to weigh up the pros and the cons. So that is cells and batteries. Like I said, it goes with this booklet here. It's the last section, but we will leave it there, and hopefully you'll rejoin me for the next video in Chemistry Paper 1. All right, thank you.